Okay, so welcome back to the diffusion and flow model the course. So last time we are discussing some kind of the boring things that probably most of you already know about some the GAN and the VAE, which are basically some the basic idea in terms of how we can make some kind of the generative models. So what we started to see from the last class is that given some kind of the large collection of the data, how we can make some kind of the model that can allow us to basically produce another kind of sample that looks like one of the data points that we have. So we started to see this kind of the problem from the statistical perspective. In terms of that, if we see those kind of the data points as kind of the samples from some certain the probability distribution, and if we have some kind of the certain form of the probability distribution, that we can consider directly just like sampling the data point from that specific distribution. So that was kind of the basic idea. Especially if the given the distribution is a form of the Gaussian, then we have seen like how we can do some kind of sampling from that. So that was kind of the basic thing. The problem is that obviously the given the set of the data points, not from the typically from the Gaussian distribution. So and also we don't know the underlying the form of the distribution for the data points that we have. So for that, like the basic idea that we discussed last time is to basically find a mapping from any kind of a simple distribution. Typically, that's the standard the Gaussian distribution, but it does not need to be this specific form. But we are basically using the Gaussian distribution because of the simplicity for many things, right? And so we are basically finding a mapping from the simple distribution to the our the data distribution in a way that the generation the process can be defined as kind of like sampling from the given the simple distribution and then mapping that data point to the one of the data points that we have, right? That was the basic idea. And we started to basically use this kind of the some kind of the terms and some kind of notations. So we are going to call this kind of the some simple distribution as kind of the latent distribution, and also using the z as kind of the variables for that. And x denotes the hourly data point, right? Then here also the question is that how are we also going to find this kind of the mapping from the latent distribution to the data distribution? And for that, basically, we are going to use the neural net. And then we discuss the two ideas, like one is the GAN and the other one is the VAE, right? So for both of the cases, first, we are defining a neural net that is like mapping the latent variable into the data point, right? That's typically called the decoder or the generator. But the key idea is that we cannot just like solely training the decoder or the generator. We also need to jointly train the another network in a way to find a kind of the property mapping. And do you remember the other network for the GAN and the VAE? The other network for the GAN, the case was basically having the discriminator, right? So we are making the decoder or the generator and also the discriminator, making them to be compete each other in a way that the output can be something that is like non-distinguishable from the real kind of data point. And the VAE case, instead of like discriminator, we are having some kind of encoder, which is learning the proxy of the posterior distribution. So that was the basic idea that we discussed last time. And to get into the idea about the variation of the posterior in the VAE, we discussed some kind of the basics about the statistics, like the marginal distribution, the expected value, base rule, like all the things, right? I guess you remember all those things, right? So these are really basic things that we're gonna basically keep seeing in the rest of all the lectures in this class. Especially for the base rule, we are basically having those terms. The prior distribution, that's basically our latent distribution, the simple distribution that we're basically starting the sampling from. And then based on this, we also learn the generator, which is basically the conditional distribution from the latent to the data points here, right? That's called the likelihood. And based on that, we are basically we want to capture this, right? Learning the probability distribution for the data points, which is called the marginal distribution. And based on all those three things, we can also define another one, which is the posterior distribution, define some kind of the mapping from the data points to the latent points, right? So those are also the terms that we're gonna keep using over all the lectures in this class. So as I mentioned from the class last week, we're going to have some kind of quiz every lecture. So the touristic quiz is that. So basically, we review some kind of the basic things here, right? The marginal thing, distribution, the basic rules, and many things. And given these things, actually, this was kind of the homework last time. Given these two distributions, P and the Q, both are the Gaussian distribution. Especially here, this is the case that Q is the standard Gaussian distribution. The mean is 0, and the variance is basically the identity matrix. For those two distributions, can you compute the KR divergence between these two? So you I guess got this answer, right? So this is slightly more the general form. For the cases like when you have the two isotropic, the Gaussian the distributions, right? Yeah, I'm gonna post this on the link, so you don't need to take the photo of this. But basically, yeah, you can see this. It's all based on the definition of the K divergence, right? And the question was some kind of for the special case when the Q is basically the standard Gaussian distribution. So in this case, now we can define the K divergence like this, right? So kind of like simple math. You're gonna keep seeing the KR divergence in the today's lecture and also for the rest of the lectures in this class. Okay, and the basic idea for the VAE, if we go back to the VAE, basically we want to basically define the mapping from the latent to the data distribution as kind of the sampling process. So now we are the decoder becomes like basically predicting the mean of that the likelihood distribution, the x conditioned by z, right? So given this kind of the prior distribution and the likelihood distribution, based on that, from the marginalization, now we can compute the marginal distribution for the data point x, right? Then the purpose of like learning the likelihood distribution with the decoder here should be basically maximizing this kind of the marginal distribution for the given the data point of the x, right? So here the question is that how can you train basically our the decoder in a way that becomes learning some kind of the likelihood distribution, maximizing the marginal distribution there, right? So we only this like single the decoding the network. It is not possible basically to compute this. So we can also actually consider computing this like marginal distribution by just taking some kind of the Monte Carlo estimate in terms of that we are sampling lots of the z and taking the sum of like this part for all the z, right? But this will basically involves like huge computation because to approximate this integral, we will need to have some loss of the z here, right? So we are not going to get into that way. Now we are going to choose the other way around, which is basically computing this marginal distribution in this form, right? Using the base rule. But here the problem is that now we don't know this kind of posterior distribution as well, right? So that's the problem. So given that we don't know the posterior distribution, what we are going to do is that instead of like directly computing this, in this case that when we don't know this information, we are going to consider this the lower bound for the log the probability of the px like this. So why is this the lower bound? We can basically easily check this out from the Jensen's inequality that we have seen last time. So this is nothing but we are basically multiplying the same thing from the denominator and denominator like this. And then now this is basically converting this into the form of the expected value while taking this probability as kind of the weights, right? So these are also the same thing. And from the fact that the log is the concave function, from the Jensen's inequality that we have seen last time, now we can see that these two should have this inequality relationship. So now from these like 4 lines, we can easily see that actually this becomes the lower bound for the log probability that we are going to compute. So what this means is that our goal should be basically finding the likelihood distribution, the decoding network, defining the likelihood distribution in a way to basically maximize the px, right? For all the data points that we have here, right? But since we cannot directly compute the marginal distribution, what we are going to do is that we are going to introduce another neural network, which is this one, right? This is called the variational posterior, which is not exactly our the posterior distribution. It's kind of some sort of the proxy distribution that kind of plays the role like the posterior, but not exactly the posterior, in a way that we can compute the lower bound like this. So given this kind of any arbitrary distribution that we are learning here, we can say that like this will basically form the lower bound, and we can basically consider maximizing the px, not exactly maximizing the px, but basically maximizing this like lower bound in a way to basically learn both the variation of the posterior and also the likelihood as well. So if we see some more details about this like elbow function, it is the elbow function. We can decompose the joint distribution here into these two forms. Right? Decomposing this into these two. And then we can also decompose like this. And then we are seeing that now the elbow function have these kind of the two terms, right? So again, we are seeing the KL divergence here, and also I think the another terms there. So the first term is called the reconstruction term. We are going to see like why is the reconstruction term, and this is the term that we are going to maximize. And the other one is basically some sort of the regularization, the KL, the divergence regularization, which will be basically minimized through the training. So here, basically, the interesting thing is that this is basically the lower bound function that we are going to maximize over training. That basically means that we are maximizing the first term, the reconstruction term, and also the minimizing the second term. So minimizing this term, can you see the meaning of like minimizing this term? Yes. So basically, we are going to make these two be the same, right? And Q is some kind of some property distribution that we are going to learn. And PZ, what is PZ? Is the latent distribution that we set as kind of the standard Gaussian distribution. So the meaning of this is that actually the maximizing the elbow basically means that we are finding some kind of some variation of the posterior distribution while making it to be close to the standard Gaussian distribution as much as possible. Make sense? So somehow we first need to find a kind of the mapping with this kind of like the variation of the posterior while making this to be close to the standard Gaussian distribution. So as this gets closer to the standard Gaussian distribution, that becomes basically we are maximizing the elbow function, which basically means that we are also maximizing the marginal distribution. Make sense? That becomes the minimizing the meaning of the elbow function here. So basically, what we can see is that we have the decoding the network here, which is defining the likelihood distribution. So we set that the output of this network to be the mean of the likelihood distribution. So basically, we are setting everything as kind of the Gaussian here for the simplicity. So when you set the likelihood distribution as kind of the Gaussian distribution, the output of the decoding becomes the mean of the Gaussian distribution. And what we need to do is that we also need to learn the proxy distribution, the variation of the posterior here, which is also modeled as another Gaussian distribution. And then in this case, now we also predict both the mean and the variance like this. And what we have seen in the previous slide is that we are basically learning this in a way that these two becomes closer to the standard Gaussian distribution. And then now we can see that actually this becomes quite close to the typical autoencoder, which is in terms of that we are having the encoder mapping from given the data point into the mean and the standard deviation of the. So the variation of the posterior is basically is learned by the network, which we call the encoder, basically mapping from the data point to the latent variables, and the other way around, from the latent variable to the data point is the decoder, right? So that's learning the likelihood distribution. So you can see that in the structure-wise of the neural network, it's quite similar with autoencoder. We are basically having the encoder and the decoder. The only difference is that using the encoder, we are not actually mapping the data points to one of the points here, but actually mapping the data points into the with the variation of the posterior like this. And then given the variation of the posterior here, we are going to sample one of the data points here, and then that will be decoded through the decoding the network, right? So that's the only difference. So we are not just directly mapping one of the data points here into the latent variable, but actually mapping this into some variation of the posterior. And based on this like variation of the posterior, we are going to sample one of the latent variable that will be decoded back to the data point. So that's the basic idea. So in the training time, how we are going to maximize the elbow function. So the elbow function was defined like this. And we have seen how we can compute this, right? So that was the quiz. So we know that this is the standard Gaussian distribution. This will be another the Gaussian distribution, right? Exactly the same form that we have seen in the quiz. So in terms of that we are having the KR divergence, we know how we can compute this, right? So the only thing is that we just need to maximize this term. And for this, like what we are going to do is that we are going to simply approximate this expected value by just taking some of the samples of the z from that the variation of the posterior distribution. So given the lots of the samples of the z, typically we just take some few samples, but to get some like better approximation, actually we need to have some more samples of the z here, right? So this becomes as computing this, right? And then the question is that how we can sample the z here, right? So z was basically the sample from the variation of the posterior, which is defined with the mean and the standard deviation here, right? So what we can do is that from the reparameterization trick that we also discussed last time, this z can be simply computed by just sampling the standard Gaussian sample and then computing this formulation, right? This is basically the mapping from the standard Gaussian distribution to any other arbitrary Gaussian distribution. So z can be basically computed based on the mean and the standard deviation that we are predicting using the encoder, and also computing this through the standard Gaussian the sample there. So given this kind of the z, what we can see is that if we plug in this into the just like PDF of the Gaussian distribution, then we can simply see that the log of the probability becomes the form of like this. That what we can see is that actually this was basically some kind of parameter that we set, right? So this is kind of the constant value. So we can ignore in the loss function. The only thing we are basically getting is that basically this form, right? So that's why basically this term is called the reconstruction term. So what we can see is that given the kind of data points of the x, we are basically learning some kind of the variational distribution. From that, we are going to sample the z here. And from this sample, when we decode this back into data point, we are going to see whether we can reconstruct given the input data point here, x here. So that is basically exactly the same loss that we are seeing in the training of the autoencoder, right? So from this, basically what you can see is that this becomes like quite the same with the training of the autoencoder. If we only see this like reconstruction term, the only difference that we are seeing is that we are basically having this like KRD divergence deregularization. So the two differences from the autoencoder to the version of the autoencoder is that we are not directly predicting the latent variable, but the version of the posterior like this, in a way that z can be sampled from that. But from the sample z, we still want to basically reconstruct given the data point x here, right? So in the sense, that is basically quite similar with the typical autoencoder structure. And here, basically, we are having some kind of the process like sampling z here, right? So why is that the sampling is still like differentiable? Because like we are not just like directly just sampling z. We are going to compute the z using the mean and the variance that the variance that we are predicting using the neural net. So still the z becomes some kind of the variable which depends on the prediction of like these two, right? So when you compute some kind of the reconstruction, the loss with this z, still the kind of the loss will be backpropagated through the prediction of the mean and the variance. So that's why basically we can train both the encoder and the decoder. And the generation the process, we can basically, so this is kind of the proxy the distribution that was basically playing the role to learn the better the likelihood. In the generation process, we don't need to use this, right? Basically the only purpose for this encoding part is basically to learn the proper the likelihood distribution. So in the generation process, we can ignore this. We just need to sample from the standard Gaussian distribution and just like map this sample throughout the decoder. So that's the basic idea for the VAE. So here one question is that should the dimensions of the input data, the point x, and also the latent variables the z be the same or not? Yes or no? Yes? No? It does not need to be the same, right? Because like all the mapping from the data point to the latent variables and also the other way around, these mappings are all defined by the neural net, right? So in that sense, it's okay to have the lower dimensional space or the higher dimensional space for the latent space. Typically for the VAE training, we set the lower dimensional space for the latent space, right? So that's the basic idea. Any questions for the VAE? Many of you would already know about the VAE, right? So what are the limitations of the VAE? If you have tried to train the VAE before. Yeah. So typical, the output that we're gonna get would be like this, right? Looks like some realistic photos, but having some blurry kind of the outputs, right? What are the kind of the problems of the VAE in terms of the formulations? So the thing is that we are still basically modeling here, everything is kind of the Gaussian distribution, right? So we are also making the likelihood to be Gaussian distribution and also making the variation of the posterior to be the Gaussian distribution, right? But here the question is that, is it okay to make it everything is kind of the Gaussian here? So that's the question. Typically, we know that we set this latent the distribution to be Gaussian, right? But typically for the data distribution that we are going to learn, the merger distribution even will not be close to any of the Gaussian distribution. It will be much more the complex distribution, right? The thing is that so the basic idea for the VAE is that we are maximizing this log probability, not directly, but basically by maximizing the lower bound, right? Then the question is that when does this like the lower bound become the same with the log probability that we are actually going to maximize? Can you guess like when these two be the same? Yes, that's the right answer. But can you also derive like when these two become zero? So I recommend you to try to really drive all the things and see when these two exactly become zero. So yeah, you can check this out later, but basically, if you basically rewrite this kind of this is called the density gap. So basically, when you have some kind of the density inequality, this becomes the lower bound, but the question is that when these two become the same. So if you rewrite all the things, actually that you can see that the difference between these two terms becomes another, the KLD divergence between these two, basically the probability distributions. Which means that the lower bounds become the tight the bound when the learned the variation of the posterior become the same with the true posterior. So that's the case. But then here the question is that would it be possible to basically have both the likelihood distribution and also the true posterior distribution as the Gaussian for the most of the cases? So in general, when you have some kind of the very complex data distribution, when we make everything as kind of the Gaussian distribution, both all the latent distribution and the posterior and the likelihood, it is typically not possible to really basically making both the likelihood and the posterior as the Gaussian. There will be some specialty cases, but in general, it's impossible to basically having the Gaussian distributions both for the likelihood and the posterior distribution. So that's the thing. In the VAE case, well, we are basically kind of like oversimplifying everything in terms of the making the likelihood also as the Gaussian and also the posterior to the kind of the Gaussian as well. But for some kind of the complex data distribution, it's actually impossible to making the likelihood and the posterior both of them is kind of the Gaussian distribution. So which means that this will be basically very bad approximation for most of the cases, like when you have some complex the data distribution. So that's basically why we are basically seeing some kind of some limitations of the VAE. Then here the question is that what else can we do? We are using the Gaussians for the simplicity, but it sounds like we need to have some kind of the parameterization, both for the likelihood and also the posterior distributions. Not as the Gaussians, but in other ways, right? But what can you do in terms of having some kind of more like the complex the parameterizations for the both of them? So that's basically what people have explored as kind of like making some kind of the loss of the variance of the VAE. And also one of the ideas in terms of making the VAE to be more complex is to make some kind of a recursive VAE like this. So this is the part that we are starting to see some kind of the new the notations here. But here the basic idea is that now we are going to introduce not only a single the latent variables, but the multiple the layers of the latent variables, starting from the x1 to all the way to the x capital T. So now we are going to slightly change our denotations in a way that we use the x for the data point and also the z from the latent variables, right? But since now we are going to have some multiple the latent the variables, we are going to switch the notation like this. Now x0 indicates the training data, the data points. And then we are having some kind of the multiple the latent variables from the 1 to capital T. It depends on like how many kind of layers that we are going to have, right? So we are having the x0 to the x1 to the capital T. And when the mapping from the data points all the way to the initial the Gaussian distribution is defined with some kind of the multiple the Markov the process. So still, while we have some kind of the multiple layers, we are still going to simplify this in a way to assuming the Markovian the process. So here the meaning of the Markovian the process is that it's like all the sampling the process, right? So basically what we are going to do is that when we sample any of the intermediate the latent variables here, the x2 for example, the sampling of the x2 will depend only on the x1, only from the previous one, which means that any of the intermediate latent variables will not depend on any of the previous ones, like the x0 there. Only depends on the one right before the step. So that's basically the assumption of the Markovian the process. So we are basically adding this kind of rules in terms of to like making the process to be simpler, right? So this means that if we think about our generation process, the generation process is basically the mapping the x capital T all the way to the x0 there, right? It was represented with the single the conditional distribution in the VAE case, right? But now we are going to have some multiple steps like this. And then the sampling of the xt minus 1 will only depend on the xt, not any other kind of the previous steps. Which means that now the generation process can be modeled like this. So we sample from the x capital T first, and then we are basically taking the product all the transition distribution from all the intermediate steps in terms like determining the probability for the output, the x0 here. Make sense? So that's basically, and you can see that now this part was basically simple the Gaussian distribution the previous way in the previous VAE, right? But now you can see that it becomes like more complex in terms of that now we are taking the products of this distribution. So still what we are going to do is that we are going to still define this like transition distribution as the Gaussian. But when you see the entire some kind of the likelihood distribution, this becomes like more complex, something that is more complex in the Gaussian in terms of that we are now taking the product of the multiple the Gaussian distribution. Make sense? So that's kind of like one way that we are modeling some more complex distribution with the more parameters. So it's not just having like one single the pair of the mean and the variance, right? We are having some kind of the multiple the transition the distributions. So even when the like single the transition distribution is basically simple the Gaussian distribution, if we see some kind of the product of like this will become some more complex distribution. So that's the basic idea. And also, the variation of the posterior will be now defined basically by taking the product of all the transition distribution. So that's kind of the same thing, but it's kind of like another way to basically parameterizing both the likelihood and also the variation of the posterior distribution. Otherwise, basically, when you define this xt should depend on all the previous states, then this will become much more complex. So now we are basically simplifying all the process in terms of the xt is basically sampled only from the xt minus 1 without seeing any kind of the previous kind of things. So this will basically make the whole process to be much simpler. So you can see that if without the Markov the assumption, here this transition distribution should not be sampling xt only from the xt minus 1, but from all the other kind of the previous states. So then that becomes like we are modeling the transition distribution in a way to see all the previously record to sample the xt. Then the training becomes like way more complicated. So the Markovian process is to make everything to be simple. The thing is that we are also going to see the non-Markovian case as well, probably sometime next week. Let's see. Any other questions?
Your process is a Markovian process, why do you only consider the back process only the one previous step state? I mean, there is two separate x1 from the x2. Why we only consider x2, not really
또
그러니까 Q가 마코비안인데 T도 하나만 얘랑
So the question is that like why do we need to model both the Q and the P as the Markovian processes, right? Is that the question? So actually we're gonna see. But here the thing is that both the P and the Q, both of them are something that we are going to learn using the neural network. So as we basically make them as kind of the non-Markovian process, the learning of like these two the distributions will become more complicated in the VAE setup. So that's a thing. So now we just because like in the VAE setup like both the P and the Q are learned using the decoder and the encoder. For both of the cases, if we start to making the X2 sampling to be dependent to all the previous steps, that will be much more the complicated kind of training. So that's the basic idea. Any other questions? But as I said, we're gonna also see some non-Markovian case as well. But let's make our life easier for now in terms of like having everything is kind of the Markovian process. For those of the cases, we can still define the elbow function as well and start to basically train all the recursive VAE through the same process. But still kind of the challenges in terms like making the VAE in the recursive way like this is that for the VAE, basically the idea is that we are learning both the Q and the P, right? Joint training of the kind of like the decoder and the encoder. And this joint training is another actually the difficulties in terms of basically training the VAE, especially the recursive VAE. So actually that's the kind of one of the motivation that we are seeing the diffusion models here. You can so over the entire class over this semester, we are going to see all different kind of the interpretations of the diffusion models, different kind of angles of like see how why the diffusion model basically works. And like one specific way to see the diffusion model is to see it kind of like one specific some kind of some variant of the hierarchical VAE, the recursive VAE. So let's get into that, the basic idea first. So from the context of the hierarchical VAE, we are going to see a kind of special case. We did like two kind of things. First, we are going to match the dimension of the latent the space to be the same with the dimension of the data points. We didn't need to match the dimensions in the VAE case, right? Because all the mappings are basically done using the neural network, right? For this specific case, we are going to match the dimensions for all the kind of the things, including all the latent variables and the data points. Everything is in the same dimensional space, right? Also making our the life easier. And one more thing is that, because this is kind of the key part. So the problem with VAE was that we are basically jointly training both the variation of the posterior and also the decoding network as well, right? So that's kind of the things, how we're going to jointly train both of them. Now the thing is that we are not going to learn the variation of the posterior. We are going to use some kind of the predefined the variation of the posterior distribution. So we are dropping the neural net parameters here. Right? So this is not learned. This will be predefined. Then the question might be is that even when we predefine the variation of the posterior, will this kind of the predefined the variation of the posterior will minimize the elbow function? So that's basically the things that we are going to see today. And given this kind of some specific the assumptions, I'm going to introduce some kind of some new terms here. By the way, so this is the part that we are going to see some kind of more complex kind of things. And actually, even more kind of issues is that, so this is for the diffusion model in this case, right? And also we are going to discuss the flow models after some few weeks. For the interpretation of the flow models, even we're gonna start to use some kind of the different notations. So basically all the notations here are basically coming from the papers introducing these ideas. Okay, even the paper was introduced in just like 4 years ago. So these are basically, as I said, very new the subject. And every paper is actually using all the different notations. So that's the kind of big problems. So here, in the context of diffusion models, we are going to use like those notations. Please keep this in mind. This is something that you're gonna keep seeing in the explanation of the diffusion models. We are starting from the x0, that's the data point, all the way to the x capital T is basically the mapping from the data point to the sample from the initial Gaussian distribution. So that was the based on the posterior distribution, right? So we're gonna call this process as kind of the fold process. Okay? So the fold process is coming from the data points to the all the way to the data points. The reason why we call this as the fold process is that that's kind of the process that we call as kind of like diffusion, like adding some kind of noise. So that's basically what we are going to see. So that's kind of the main thing. And as I said, this is the transition distribution that we are going to predefine. So let's see how we are going to predefine. And the other way around, the mapping from the latent to the data points there is the reverse process. And that's the kind of the process that we are going to learn. So still that we are learning this distribution, not this one. So this transition distribution will still be learned. And this is basically our generation process, right? Our generative process is basically the reverse process, starting from the x capital T all the way to the x0 by basically doing some kind of recursive desampling through the reverse the transition distribution here. So that's basically what we are going to learn through the using the neural network. And here the key idea in the diffusion model is that basically how we are going to define this fold the transition distribution here in a way that the variation of the posterior will be defined as kind of the product like this, right? And that specific variation of the posterior should minimize our elbow function. So here the key idea is to how we define the this transition distribution in a way that this the maximizes our elbow function. So that's the key thing. So actually the thing is that there are multiple ways to define this like for the transition distribution. So let's see the single case first. Later, we are going to see more cases. But let's first see the simple case. So this is the kind of our definition of the for the transition. So over the time, over the kind of the for the process, we are basically seeing that the t is kind of the time. Time is basically increasing from the 0 to capital T in the for process. So you can say that it's kind of like the over time some kind of the process, some iterative the process. And then over time, we are going to set some kind of parameters of the beta t here. And based on the beta t, we are defining some kind of the Gaussian distribution like this. So still, we are making everything like the Gaussian, right? So we can see that the meaning of like this kind of the transition the distribution is that so basically the beta t is basically increasing from the 0 to some kind of the numbers. So the thing is that the beta t is basically non-decreasing function. Over time, the beta t will be increasing. But still, we are going to keep all the numbers to be small enough, like 0.0 something. But we will be some kind of the non-zero number and also keep increasing like this. So when this is basically zero, what you can see is that this is nothing but just like having the standard Gaussian distribution, right? So if the beta t is zero, is basically, it's not the standard Gaussian distribution. So it's basically zero, then it's basically some kind of the direct delta D distribution in a way that the sample of the xt should be the same with the xt minus 1, right? But as you basically increase the beta t here, what we are seeing is that we are adding some small the Gaussian noise, while basically shifting the mean to be closer to the zero, right? So this is kind of doing some kind of shifting to get closer to the zero. The mean is getting closer to the zero, right? While basically slightly adding some more kind of the Gaussian noise. So you can see that this is kind of the process that we are repeatedly adding some kind of the Gaussian noise while increasing the variance like this, and also moving that the kind of the terms to be closer, get closer to the mean, but not exactly to the mean, right? Because like all this kind of the beta t to be some small numbers, right? So this is kind of the one specific way that we are defining the for the process. And you can also still see that there are some kind of the parameters of the beta t. Actually, you will need to implement this in the assignment one. So you will need to see what's the meaning like this. And depending on how exactly we also set the beta t, you will see some kind of the difference in the performance. So there are lots of kind of options for the beta t. But basically, if you satisfy this condition, these are basically increasing, non-decreasing decreasing function, and also making all these numbers to be small enough, then it should work. But there are still kind of the bunch of the options. Even you can consider like all the beta t to be kind of some neural networks of the variables in terms of the we are learning over the training. We can set these like beta t to be constant and also linearly increasing and also ranking the cosine functions. And so there are a bunch of the options. But in any case, the only condition is that we just need to make all this beta t to be small enough while making it to be non-decreasing function. Okay? So keep this in mind. So this is the hourly definition for the fourth the transition distribution. Why this should be non-decreasing? So we're gonna get into that. So yeah, so that's also the things. So we're gonna discuss some kind of the more details of like those definitions probably also the next time as well. There are so many kind of things to discuss. So here basically all the kind of the idea is that we are predefining the fourth the transition the distribution in a way to make it all the variation the posterior to be something that is maximizing the elbow function. So let's actually see whether this exactly really maximizes the elbow function. So if we get back to the elbow function, actually, once we have some kind of the multiple kind of the layers in the recursive kind of VAE, the elbow function becomes quite complicated like this. So I'm going to skip some details here. For more details, we check out the references there. But the thing is that if we decompose the elbow function into as we have done in the VAE case, then we can still see some of these kind of like three types of the terms. The first one is the reconstruction term that we have seen in the VAD case. And the other one is the priority matching term, which is the same with the KAIST term. And then we're having one more term, which is the consistency term, which is basically basically nothing but, making these two, the distributions to be the same. So that's basically why we are calling basically this kind of the consensus term. So we can consider basically computing this consensus term. The problem is that, as you can see, this term is basically involving two random variables. We are basically having the two latent variables here, and it's basically maximizing this term to be quite computationally very expensive. So actually, we are not gonna exactly compute this term. We are going to consider the other way around to decompose the elbow into the other kind of the terms based on this fact. Can you see like why these two are the same in our case? Yeah, because of the Markovian assumption, right? So since we assume that all the process kind of the Markovian process, we are going to treat these two be the same. Basically, now xt becomes independent of the sample of the x0. So that's kind of a good thing of like having the Markovian assumption. Otherwise, actually, these two cannot be the same, right? Xt should be dependent on all the kind of the previous kind of states. This making the computation to be much more complicated. So with this kind of the Markovian assumption and having these two be the same, what we can see is that now we can decompose the elbow function into the different way. So having different three terms from the same elbow function. So what you can see is that we are still having the reconstructed term here. So we are going to see these like the one by one. Let's see the first one. So this is the same the reconstructed term, and this is basically reconstructing the x0 from the x1, while we are having all the other kind of the latent values from the x capital T, right? So this is like only for the final step of the reverse process, and also in practice, the magnitude of like this loss term is like much smaller than the other terms. So we are going to simply ignore this term. So that's the thing. The second thing is about the D-scalar divergence. So this is kind of the main part. So what we are going to see is that now we are going to basically see. So this is basically the decomposition of the elbow function, which means that, this is the negative the elbow function, which means that we are going to minimize this. So can you see the meaning of the like minimizing this term? What's the meaning of like minimizing this term? So we are basically going to minimize this term, right? The thing is that actually all the transitional distribution for the default process was predefined, right? And this is like sampling x capital T to the x0. So sampling the last one from the very beginning one of the default process. This will be also derived from the definition of the transition distribution. Then what we need to see is that, so this becomes the variation the posterior, and we need to see whether the variation the posterior will be the same with the pxt. What's the pxt? It's the standard Gaussian distribution, right? So this is the latent distribution. We are going to, so our degeneration process is like sampling the xt here, sampling the standard Gaussian the sample, and the mapping to the x0, right? So this is the fourth process, sampling the x capital T from the x0, right? The fourth process. And this is based on the hourly definition of the transition distribution. We need to see now whether this the variation posterior based on the hourly definition should be the same with the standard Gaussian distribution. So let's see whether we define it in that way. So the question is so whether these two are the same, right? So let's see. So basically, recall that we defined the full transition like this. We're gonna do some kind of the simple math here. While we use the beta t, let me just quickly replace some of the beta t with the 1 minus beta t, the alpha t here. So when you see the alpha t here instead of the beta t, now we can see that this is the non-increasing function, right? It's basically decreasing over time. And based on this, what we are first going to see is that So let's see, like we only defined this like the one step of the transition distribution. Right? We know how to sample the xt from the xt minus one, right? But when you think about some kind of the accumulation of this kind of like the transition distribution, can you directly sample the xt from the x0, which means that would there be some kind of the closed form of this conditional distribution, xt conditioned by the x0 from the all the sequence of our default the transition distribution? Do you think that we will be able to get some kind of closed form for that? Or not? We should have the closed forms to basically see whether this matches the standard Gaussian distribution. So actually, the answer is obviously yes. We're gonna derive some kind of the closed form this for the conditional distribution. And for that, basically, what we are going to quickly see is that. So let's get back to some basics of the Gaussian the distributions. So basically, let's consider like we are having the sample from the x1, which is from this specific the Gaussian distribution, and the x2 from this specific distribution. Then can we also express x1 plus x2 as kind of the sample from the another the Gaussian distribution? Yes, or no? Yes. The answer is yes. Basically, we can see that x1 plus x2 is kind of a sample from this specific Gaussian distribution. So now you can see like why we are using the Gaussian distributions, right? There are many kind of good properties in the Gaussian distributions in a way that we can play like this. So you can see here, like when you have the x1 and x2, both of them are basically sample from the different Gaussian distributions, right? And if you take the sum of these two, then we can see that that is kind of the sample from the another, the Gaussian distribution. How about this? Now you have some kind of the two the samples from the same, the standard Gaussian distribution. And scaling them to define the x1 and the x2. In this case, what's the distribution for the x1 plus x2? You know the answer, right? Yeah. So basically, actually, we can say that x1, the x2 is also kind of the sample from the another the Gaussian distribution, not having the identity as the variance, but basically having this like the scared sigma 1, scared sigma 2 as kind of the variance. For in this case, from the things that we have seen in the previous slide, we can also see that x1 plus x2 is also the sample from this specific the Gaussian distribution, right? So these are some kind of very basic properties of the Gaussian distributions. And based on that, let's see this. So this was basically our definition for the transition distributions, right? Sampling the x1 from the x0 and sampling x2 from the x1. The good thing is that we define everything as kind of the Markovian kind of assumption in a way that the x2 does not depend on the x0 here, right? So making our life easier, right? So based on that, can we also define the get the closed form for this conditional distribution, sampling the x2 conditioned by the x0. So just merely to plug in all the things that we have seen in the previous slides. So let me give you like the 5 minutes, 3 minutes to see whether you can get some kind of answer for this. Try yourself what you can get from this. So if we see like what you get, and this is the thing, right? No, from the, sorry. So yeah, you can basically derive all the things in terms of we are here replacing the xt minus 1 with this formulation. And then if you like rewrite all the things, you can see that it's combining these two terms. These are all some kind of the Gaussian samples from the Gaussian distributions, right? From this, you can see that actually I think I missed some of this slide here. Imagine this. Yeah, from this, just rewriting x1 with the formulation and just like combining these two Gaussian distributions, then what you can see that actually this conditional distribution x2 conditioned by the x0 can be written based on the Gaussian distribution. Okay. So this basically shows that for any kind of the, while we defined this like one step the transition distribution, from this, now we can derive the closed form of the, this what I'm going to call this as the fourth jump. We are jumping from the x0 to the xt here, sampling directly xt from the x0. And this can be done by this like this specific Gaussian distribution. So that's, you can say like now we are basically defining the fourth transition distribution in this way. So as you can see, like basically the xt can be now directly sampled from the x0. So actually you can see that while we define the fourth process as kind of some sort of the iterative process, actually it does need to be iterative sampling. We can actually directly sample the xt from the x0 for the forward process, probably not for the reverse process. So that's kind of the thing. So based on that, basically what we can see is that, so what we want to see is that whether this, the variation in the posterior, it's not the variation anymore, right? Basically, whether this posterior, the x capital T from the x0, whether this becomes close to the standard Gaussian or not, right? So this will basically define like this. And then what we have seen is that we set the beta T to be some kind of the small number in the 0 to 1 range, right? And when this is defined like this, when you take the product of some kind of the number in the range from the 0 to 1, smaller than 1, if you take the product of the last of such kind of numbers, you're going to see that this will get closer to the 0, right? Which means that as we have some kind of the lots of these, some kind of the multiple steps in the forward process, naturally by definition of the forward to the transition distribution, this posterior distribution will get closer to the Gaussian distribution, the standard Gaussian distribution. And that is aligned with the hourly elbow function, right? So by definition of the forward process, that is basically naturally maximizing the hourly elbow function. So you can see like why we defined for the process in that way. So next time I'm gonna continue basically. So what we are going to do, how we are going to deal with like this term. But you can see that here all the basic idea is that we are starting from the VAE. We are modeling the likelihood and the posterior as kind of the Gaussian distribution, which are basically not sufficient for the many complex the data distribution. So that's why we start to see some kind of the hierarchical, the recursive way making the VAE. But the thing is that we still don't want to learn both the likelihood and the posterior. So now we are going to fix the posterior in a way that naturally basically maximizes the elbow function. And then we're gonna only learn the likelihood distribution. So that's basically like one specific angle to see, interpret the diffusion models. Then we're gonna keep discussing this idea in the next Wednesday.